But we have better ways to do that. Why go through all this trouble and expense just for an elemental analysis? You can do that by combustion. So it kind of sat there until some organic chemists about 20 years later got hold of it and realized, as technology got a little better with magnets and radio frequency technology, particularly around World War II, where a lot of sophisticated radar technology developed our electronics in big leaps and bounds, they discovered that not every hydrogen in an organic molecule has exactly the same magnetic property. If you look just at the hydrogen nucleus, it should always be the same. Nothing changes. It's a hydrogen nucleus, whether it's attached to a carbon or attached to an oxygen. So it should be at the same frequency. But they noticed that there were very subtle differences in the frequencies at which chemically different hydrogens would absorb energy. So at 11.7 Tesla, it was always almost exactly 500 megahertz. But there was a slight, almost imperceptible variation that with better technology they realized was due to environmental effects around the nucleus. Hydrogen has a lot around it. In particular, it has electrons around it. So how does that affect the way the magnetic field interacts with the nucleus? Well, the same way that you get affected if you're on your cell phone and you walk behind a tall building. Your signal dies. There is an interference from this external signal getting to your cell phone receiver. The same thing happens with nuclei in organic molecules that have this very complex environment of electrons and other nuclei around it, etc. So if you take something like ethyl alcohol, instead of the original impression was that you would just see one signal at 500 megahertz saying that you have hydrogen present, what you're really seeing is three different frequencies of resonance, but at only parts per million differences. So like one hydrogen would be at 500.0000002 megahertz, the other one would be at 500.0000015 megahertz. And because they weren't seeing that tiny difference, they thought it didn't exist. But once we realized it existed, that's when NMR just exploded, because you do get three different signals for the three chemically different types of hydrogens. And you can even, with experience and theory, figure out what kinds of environments are around those hydrogens. So NMR really exploded at that point as a way of telling not just that you have hydrogen, but how many different kinds of hydrogens do you have, what are those kinds, how many of each kind that you have, and even what kinds of neighboring hydrogens would a particular kind of hydrogen have. Like this, we label this ABC, three different chemical types. The A-type hydrogens have two chemically different neighboring B-type hydrogens. So you might say, well, I'm going to see three peaks at different frequencies. Very, very slight different frequencies, but I can measure them. We can do this now very easily. So I get three peaks. In fact, the relative sizes of the signal would mirror this. So this peak, let's say it's this, well, let's say this is the CH3, this is the CH2, and this is the OH. This one would be 3 to 2 to 1 in terms of the relative areas underneath those peaks. They're not drawn to scale, but electronically, you can measure the areas on the peaks very easily. So that would come out to be 3 A hydrogens to 2 B hydrogens to 1 C hydrogen. So 3 chemically different types of hydrogens in the ratio of 3 to 2 to 1. I would also see not just 3 peaks, but just to focus on the A peak would actually appear not as a single line, but with the super resolution that I have, I could actually see that it's 3 closely spaced lines, or what we call a triplet. The triplet is due to a phenomenon called spin-spin splitting, where the A hydrogens are affected by the 2 chemically different neighboring B hydrogens. Splitting. So what you would expect to be a single peak looks like it splits up into a bunch of closely spaced lines. The spacing is always identical, like a picket fence. And in fact, there's a regular, predictable intensity of the pickets in the fence.
What does that say? School one? I forgot to get that. On the left. Something one.
You see doublets,
It was like school.
which are not 2 separate peaks, but 1 peak undergoing spin-spin splitting into what we call a doublet. You see triplets, you also see quartets, pentets, sextets, septets, heptets, octets. They're all called multiplets because, again, it's really one resonance, but it's artificially split to your view into a multiplet. And the intensity of the lines, as I mentioned, is predictable. Now, you never bother to measure it, but one thing that alerts you to the fact that you're looking up at a multiplet, besides the picket fence even spacing, is this sort of crescendo effect or chandelier effect towards the middle, or candelabra effect, I should say, towards the middle. Gets bigger in the middle, it fades out at the end. And actually those numbers come from this.
Conspiracy. Oh, that's math, isn't it? Like
Anybody recognize that?
Pascal's triangle? Is that what it is?
Called Pascal's triangle.
Yep.
Oh, very good.
Associated with the coefficients of a linear expansion. If you have 1 peak, it's 1. The next level is a 1-to-1 doublet. The next level is a 1-to-1 triplet. And the 2 is the sum of the 2 numbers right to left at the level above. 1, 3, 3, 1, 1, 4, 6, 4, 1, etc. Now, you don't have to figure that out mathematically, but what it gives you in a multiplet is a set of lines that are equally spaced that rise to a maximum in the center, sometimes with a little distortion to one side. Now, this triplet right here is described as having n+1 lines, where n is the number of chemically different neighboring hydrogens. Now, this is the most confusing thing about NMR in the beginning, the spin-spin splitting. It happens to be the most powerful thing in NMR in terms of molecular structure determination, but it's one of the most confusing. That CH3 that we're calling A has two chemically different neighboring hydrogens, B. The C hydrogens are further away. Neighboring means, think of it like a big U. Neighboring means right on the next carbon. Any further away, it doesn't affect it. But
Upside down is the word.
they have to be on neighboring carbons and chemically different. If they're chemically equivalent, they don't do this spin-spin splitting to each other. And it is reciprocal. I'll get to that in a moment. But A has two chemically different neighboring hydrogens, and so the signal that I'm expecting for A, instead of being a single line, is going to be split into n+1 lines, or 2 plus 1 is 3. So A is the 3 A hydrogens on the methyl, but it's split into a triplet by the two chemically different neighboring hydrogens. So when I see that triplet, that says to me, whatever hydrogen type this is, it has two chemically different neighboring hydrogens. So this peak isn't the peak for these two hydrogens, but this peak is a triplet because these two hydrogens are affecting it. Now, these two hydrogens are also affected by these three. And so spin-spin splitting is reciprocal. We'll look at this in more detail. Well, let's say you're the methyl, and you look next door. There are different hydrogens there, right? Different from you. Now, I think the confusion is I'm not saying they're different from each other. I'm saying they're different from you. So, if you've got, let's say, two brothers and they're standing next to you, how many different brothers are next to you? Different from you. Two. How many different people are next to you? Two. Right. They may be equivalent to each other, they may be twins, but they're two different from you neighboring hydrogens. So again, that's a good point. Neighboring and chemically different means different as a set. So the A hydrogens are different from the B hydrogens. And there are two chemically different neighboring hydrogens for A. Now B is more complicated because it has not only A hydrogens that are neighboring, but the C hydrogen is neighboring. So what would you see for B?
Me and her saw that the other night outside we went to this
So instead of a single peak for B, B is going to be split by the three neighboring A hydrogens and the one neighboring C hydrogen. Now here's where it gets really complicated. You can't lump them all together as chemically different neighboring hydrogens. Say there are 4 chemically different neighboring hydrogens. And the reason for that is that this neighboring business is like spin chatter. So the nuclei are actually talking to one another, they're communicating spin information. So if I'm an A hydrogen in the lower energy state and I'm about to flip to the upper state, it makes a difference whether my neighbor is in the lower state or the upper state. And there are 2 hydrogens there. So the origin of the spin-spin interaction is this, what's my neighbor doing? Is my neighbor in the upper state or the lower state? And I've got two neighbors. I could have one of my neighbors in the upper state and the other in the lower state in two different ways. I could have them both in the lower state or both in the upper state. That's where the triplet comes from. Both in the lower state, both in the upper state, and the one in the middle is one in the upper state and one in the lower state. So it's all spin chatter. Yes.
Well, in this case for Z, it would have two different hydrogens, or four, because there's three on the methyl and one.
Well, the simplest case would be if you lump them all together and say B has 4 chemically different neighboring hydrogens. How many lines would you see? Five, n plus 1. Right, B has 4 chemically different neighboring hydrogens. N plus 1, where n is the number of chemically different neighboring hydrogens, is 5. So you see something that looks like that.
Pay attention.
Now, that will only happen if A and B are talking at the same volume, if you will, as B and C. This chatter that goes back and forth has an effect on the space in the picket fence. If the two hydrogens are yelling at each other really loud, the space gets really wide. If they're just whispering to one another, the splitting space gets very small. If you've got two chemically different neighboring hydrogens and they're talking at about the same volume, this is an oversimplification, then you'll see this. So you're hearing them equally, and it's just like 4 voices coming at you, and you split into 5 lines.
I have to go to school late.
If the spin chatter is equivalent for all of them. Now, if some are talking more intensely than others, then the A hydrogens, let's say, could be split into 3 lines. So here's A, and then it's split by B into a triplet. But B, I'm sorry, we're looking at B. B is split by A into a quartet. And B is split by A into a quartet, 3 plus 1. But B is also split into a doublet by C. So each of these lines will split so you get a doublet of quartets, 4 lines, each one split into 2. 4 times 2 is 8. 1, 2, 3, 4, 5, 6, 7, 8. Yes?
That's if the chatter's not equal, right?
Right. And what this translates into unequal is very chemically different neighbors, like a CH3 and an OH. This is really going to be more complicated. The 5 lines, where does that simplification come from? Why would you see less than 8 and in particular 5? Well, it's hard to draw, but you have to keep your spacing constant. See the spacing between that quartet. If you do the second splitting of each line into a doublet with exactly the same spacing, some of the lines overlap. And instead of seeing 8, you see 5. If the second splitting is bigger or smaller than the first, then the lines peek out from each other and you see more of them. So the bottom line is you'll see somewhere between 8 and 5. Sometimes spin-spin splitting is so complicated that you need a computer to sort it out. But the software has that built into it for NMR. And it's very important to be able to do that and sort out spin-spin splitting, because it tells you what is around a particular type of hydrogen. That type of proximity information is very rare. Yes?
Can you explain why the second splitting you guys? What splits the second one?
Well, the splitting is going on somewhat independently. So C is talking to B all by itself, and A is also talking to B all by itself. And the net effect is represented by these splitting trees. So if this is the CH3 splitting A into 4 lines, then C is going to split each of those 4 lines into 2 lines. So you get a doublet of quartets, or a quartet of doublets, however you want to look at it, 4 times 2. Now, most of the time it's fairly simple. And to make your life even more miserable, I'm going to tell you that for ethyl alcohol, this OH often doesn't couple with the other hydrogens. In other words, the C hydrogen there often would be invisible to the B hydrogen because of exchange, hydrogen bonding of an OH causes the hydrogen on that oxygen to literally skate all over the place like a hockey puck on the ice. Hydrogens don't stay on a particular oxygen. They keep jumping from one oxygen to another. So it's like the hydrogens in the middle don't have a chance to couple in spin-spin splitting with an OH if its exchange rate is very fast. If it's sometimes there and sometimes not there. Probably 99% of the time, if you take an NMR, proton NMR of ethyl alcohol, you'll see a triplet and a quartet. As if this were the only spin-spin splitting going on. So this would be a quartet, I'm sorry, a triplet, and this would be a quartet. C would not get involved. Particularly if you have any acid present or any type of catalyst that increases the rate of exchange of the OH. And I have to tell you that OH is a particular problem in NMR, in hydrogen NMR. It won't sit still. Because of its exchange rate and its acidity, it's all over the place. So it's not like a CH or even an NH. It's all over the place.
Must.
Pardon? So most of the hydrogen is just acid-base chemistry and hydrogen bonding. It's just, in water, for instance, a particular hydrogen does not stay with a particular water molecule. It moves all over the place. It's just a network of basically zillions of hockey pucks bouncing all over the place.
It's hard to
That's
draw.
why water has such strange behavior. OH is very weird.
8 was the number to maximum result
Yeah,
of
right. So if you have chemically different neighboring hydrogens of different types, you can lump them all together and use the n+1 rule as the minimum number of lines that you would see. Or you can multiply them out as the maximum number of lines. So if you had 3 of one type and 2 of another, the 3 would cause a quartet, the 2 would cause a triplet, 4 times 3 is 12. Something between 12 and 6 lines. It's not that hard, you'll get used to it. And these are the patterns that you see all the time, doublets, triplets, and quartets. Those are the most common
I
patterns.
just finished 5.
Because a doublet
I think so.
Oh, wow.
comes from the simple case where
Have you read the book?
you've got one hydrogen next to one other hydrogen.
Book.
So A splits B into a doublet, B splits A into a doublet. So you've got 2 doublets. It's always reciprocal. Spin-spin splitting comes in pairs.
If you do a lot.
So that would be the doublet. The triplet would be, you've got two chemically different neighboring hydrogens. And it doesn't matter how many A hydrogens you have, whether it's 1 or 2 or 3, A is split into a triplet. Don't confuse the area underneath the peak, which is how many hydrogens, with the spin-spin splitting. So, for instance, if I had this,
Bless you.
A would appear as a 1 hydrogen triplet. You can also have a 2 hydrogen triplet or a 3 hydrogen triplet. You can't get more than 3 hydrogens on a carbon unless you have methane, so it's not that hard. So don't confuse spin-spin splitting with the areas underneath the peaks. This spin-spin splitting here is caused by the 2 chemically different neighboring hydrogens. You can look at it as a cosmetic effect, cosmetic alteration. Instead of a single peak, you're getting a triplet, but the total area is still 1 for that 1 hydrogen. Now, and the quartet comes from a hydrogen that's next to a CH3. So the A hydrogen is split by 3 chemically different neighboring hydrogens into a quartet. And you can have 1A or 2 A's, doesn't matter. That's the size of that peak for A. But appearance-wise, it would be a quartet. Now, there is one additional one that you see quite often.
I got that if you needed to be erased.
And that's this so-called isopropyl fragment. How many chemically different hydrogens do we have here? 2. There are 6, a set of 6 chemically equivalent A hydrogens. Okay, so that's all the same. And then 1 chemically different B hydrogen. So how many, forgetting spin-spin splitting, how many resonances should I see in the NMR? 2. 1 for each chemically different type of hydrogen. Now, don't worry about where they would appear, but let's say this is HB and this is A. Now, A is 6 times the area for B, because there are 6 A hydrogens and 1 B hydrogen. So when you do the integration, you actually get numbers underneath the peaks. It will say 6 to 1, if you're lucky. If there are other complications, it might say 12 to 2. Or 600 to 100. It's only the ratio that's accurate, 6 to 1. But it can be any numbers that amount to a 6 to 1 ratio. If the person running the NMR is doing it properly, it will be 6 to 1. But sometimes that gets fouled up. The ratio is always correct, but sometimes the numbers are wrong. So if you see 12 to 2, that's probably not correct. Hydrogens come as a single hydrogen on a carbon or a CH2. So if you see 2 chemically equivalent hydrogens, that's a CH2. They come as CH3s. If you see 3 chemically equivalent hydrogens, that's a CH3. If you see 6, that's 2 CH3s. If you see 9, that's 3 CH3s. So you have to use some common sense. Hydrogens just come in certain bunches. CH3s, CH2s, and CHs. But you can have a couple of CH3s. So if I saw 6 hydrogens to 1, I would not conclude that this is 6 different hydrogens. They're all the same, and so I must have 2 CH3s. Now, the appearance would actually be like this. The B hydrogen would show up as how many lines? B is split by A, 7. N plus 1, where N is the number of chemically different neighboring hydrogens. So if I'm looking at HB, it's going to be a very crowded, very tiny multiplet, because all of this is one hydrogen still, split over all of the peaks. It's like chopping down a tree. You've got exactly the same amount of wood, it's just a lot smaller. Now what about A? How is A going to appear? Doublet, but a 6 hydrogen doublet. So to try to be proportional, probably will look like this. Because I have 6A hydrogens. That never changes. Whether it's a singlet or a doublet or a triplet for the peak, the area remains the same. So a heptat and a doublet is a dead giveaway for this isopropyl group.
What the hell? Habitat. Damn. It's really complicated what he just drew.
You drew 7 on a line, so that for HB. And then a doublet for.
This should be, this should be like an art major class.
CH3, CH2, which is even more common, is a quartet triplet.
An art teacher. It's the last time I accept Kool-Aid from my art teacher.
Quartet triplet.
One of the worst
A is
acid
split
trip of
by
my
a
life.
triplet into a triplet by the B hydrogens. The B hydrogens are split into a quartet by the 3 chemically different A hydrogens. This is not simple. Unless you study this and work some spectra, you will be totally confused by this. Happens all the time. Don't just look at it. You've got to really take ownership of this. And the bottom line is, can you read structural information from a spectrum? And to do that, you have to understand what's going on. And spin-spin splitting is one of the main things that's